Imagine a world where harmful messages hide not just in words, but in images combined with text. Detecting such toxic content requires advanced techniques that go beyond traditional methods. This is the challenge my research addresses. Good day, everyone. I am Paula Mendoza from the Technological Institute of the Philippines. Today, I am pleased to present my research titled Enhancing Multimodal Toxic Content Detection in Clip Models via LoRA Fine-Tuning and Optimal Fusion Strategies. Online platforms, the rising challenge of detecting toxic content online, which increasingly appears in complex multimodal forms, combining images with subtle hate symbols and coded textual cues that evade traditional unimodal detection methods. Existing large pre-trained models like CLIP show critical performance gaps due to dataset scarcity, biases, difficulty recognizing fine-grained visual details, and shallow fusion image and text modalities. Despite advances, prior research lacks comprehensive evaluation and direct comparison of different multimodal fusion strategies on label datasets specifically created for hate and toxic content detection. This study fills that gap by creating a novel, balanced multimodal dataset and leveraging low rank adaptation or LoRA to fine tune, adapt, and robustly train large models such as CLIP, VisualBERT, and LXMERT. Through rigorous experiments comparing early, late, and attention-based fusion approaches, this study aims to identify the most effective fusion strategy, significantly improving detection accuracy and generalization, thereby advancing reliable and interpretable multimodal toxic content detection in real-world scenarios. Based from the related literatures, CLIP or contrastive language image pre-training demonstrates remarkable strength from its large-scale pre-training on diverse image-text pairs, which enables it to capture intricate semantic relationships and excel in zero-shot capabilities for vision and language tasks requiring integrated understanding of text and images. This flexibility allows it to outperform traditional encoders through fine-tuning or VNL pre-training, delivering competitive results on benchmarks like visual question answering. However, the original model struggles with toxic language and hate symbols in user-generated content, often missing subtle, context-dependent, or culturally specific hate speech due to broad training biases, false positives, or negatives in sensitive contexts, lack of external knowledge integration, and inadequate simple fusion for resolving conflicting multimodal cues in memes. This research paper details various multimodal fusion techniques for effectively detecting toxic content by combining image and text data. Early fusion involves blending features from both modalities at the initial stage, allowing the model to learn integrated cross-modal cues deeply. This approach often captures the complex interaction between visual and textual elements, as evidenced by studies showing that early fusion outperforms simpler late fusion techniques where modalities are processed separately and combined only at the prediction level through averaging or weighted sums. Attention-based fusion dynamically weights modality contributions using asymmetric attention or symmetric attention, with symmetric attention offering richer integration but requiring careful tuning. The paper highlights models like CLIP, VisualBERT, and LXMERT with unique fusion architectures. CLIP aligns image-text pairs in shared embeddings, space, and performs best when its features are well fused. while Visual BERT extends the BERT architecture for early fusion of images and text, enhancing understanding for their relationships, while LXMERT encodes modalities separately but merges with cross-attention layers, enabling joint reasoning. Fine-tuning greatly improves this model's performance on toxic detection tasks. For this study, we created a novel balanced dataset of around 4,659 multimodal samples combining ADL or anti-defamation league images with curated hate images with curated captions and non-hate data. While we utilizes in this study LoRA or low rank adaptation fine-tuning, which efficiently adopts large models such as CLIP, Visual BERT, and LXMERT to small data sets by injecting low rank matrices into key layers, freezing around 99% plus, preventing overfitting, and enabling top convergence in just less than 10 epochs with near zero loss. This research reviews fusion techniques for toxic content detection, combining image and text data to capture interactions like ironic text with provocative visuals in hateful memes. As a result, early fusion integrates image and text features at the input stage, enabling the model to learn combined representation that better captures subtle cues. Studies show that it achieves higher accuracy compared to the other methods. Attention-based fusion dynamically weights relevant parts across modalities, asymmetric versus symmetric, with symmetric nearly fusion results at around 95%, but needing tuning. And late fusion handles each modality independently, then merges outputs via averaging or weighted sums, simpler but risks losing integration benefits with poorer performance. Therefore, based from the following fusion strategies, early fusion excels in metrics like precision, recall F1 score, fine-tuning prevents overfitting on small data sets, baselines without fine-tuning hover near 50% accuracy. So I will now be presenting the following confusion matrix results. This figure presents the confusion matrix results of CLIP with different fusion techniques, such as the early fusion, the late fusion, and the attention-based fusion. On the next table here, the previous figure and this table here showcases the results of the fine-tuning CLIP with different fusion strategies. And based from our results here, it shows that early fusion is the most effective technique for fine-tuned CLIP in this classification task because it achieves the highest accuracy value of 97% for precision with 97.55%, recall of 96.95%, and the F1 score with 97.25%, with only a handful of errors in its confusion matrix, such as 4 false positives, 5 false negatives. So this clearly indicates that that integrating multimodal features early in the model pipeline provides a strong balance, precision, recall. We have here the figure that presents the confusion matrices for Visual BERT and LXMERT. So before and after fine-tuning on classifying non-hate and hate content, the baseline models struggled. Visual BERT actually labeled everything as hate, which gave it a perfect recall but zero precision, with no correct non-hate predictions. While LXMERT did a little better but still tended to overpredict hate, wrongly labeling some non-hate samples. So this shows that just relying on pre-training isn't enough for this specific task. So this table shows the fine-tuning, how the fine-tuning is essential for good performance in visual BERT and LXMERT models. Without fine-tuning, baseline models perform poorly with high recall but low precision, leading to false positives and overall accuracy near random chance of 50%. After fine-tuning, visual BERT achieves 97.26% accuracy and an F1 score of 97.18%, while LXMERT performs even better with 99% accuracy and an F1 score. Both fine-tuned models reach perfect precision and high recall. As a conclusion, fine-tuning with LoRA dramatically enhances the performance of visual BERT and LXMERT in multimodal hate speech detection, converting their pre-trained baselines marked by high recall, low precision, and near random accuracy into exceptional results with near perfect accuracy, precision, and balance across metrics. Among these fusion strategies, early fusion emerges as the top performer for integrating image and text features, as achieving superior accuracy, precision recall, and F1 scores, closely followed by the symmetric attention-based fusion, while late fusion and certain attention variants lag due to ineffective learning and poor generalization. So these outcomes, consistent with rigorous evaluation in the study's results, highlight LoRa's value for stable adaptation on limited data sets and stress the importance of task-specific fine-tuning, high-quality multimodal data, and optimal fusion for developing robust toxic content detection systems. Again, fine-tuning with LoRA and optimal multimodal fusion unlocks the true potential of vision language models, transforming them into precise, balanced defenders against toxic content in our digital world. And that concludes my presentation. Thank you very much for listening.